So welcome to this session, everyone. This is part two of our advanced regression analysis. We, as part of part one, covered some ground. Just to tell you on what we have discussed, we tried to understand optimization. And the reason why we try to understand optimization is because we wanted to understand ordinary least square and how we minimize sum of squared error. And this gave rise to our ordinary least square technique, which is nothing but linear regression. Okay. Once we had linear regression, we also try to understand the interpretation, pertaining to linear regression, because that is the beauty of regression algorithms. Then we had a brief conversation around logistic regression equation, how we arrive at that, where we have P probability of event occurring, 1 minus P probability of event not occurring. This is odds ratio. When you take a log, it will be called as logit transformation. And we also try to interpret the results. And we also spoke about interaction variables. We also try to understand about confounding variables. And we also spoke about moderating variables. These are the various aspects that we have spoken about. And all these sessions which are being conducted would be placed on your learning management system. Okay. So now we have to proceed further with the next set of algorithms. If your output variable is continuous, we proceed further with linear regression. If the output variable is discrete, and if you have two categories, then we proceed further with logistic regression. The moment you have your output variable, which is discrete, in more than two categories, if it's categorical data, and if the data is nominal data, then we proceed further with multinomial regression. If you have ordinal data, we proceed further with ordinal regression. If the output is discrete and count, then we either proceed further with Poisson or negative binomial. And in certain use cases, if the output variable is count, discrete and count, and if you have excess zeros to deal with, then you proceed further with zero inflated Poisson or zero inflated negative binomial or hurdle models. This is a high-level picture that one should be aware of, or we should be aware of this high-level picture. Of course, there will be some amount of math that I wish to, write and pose that some amount of math. I would try to explain maximum likelihood estimation in the context of Poisson distribution. Okay. So multinomial ordinal, we will just understand some amount of theory and we will proceed further with the code. Post that, I'll get into some math derivations. Once I'm done with the math derivations, we will proceed further with Poisson. And of course, there will be theory and negative binomial sum theory, and then we'll get into the Python programming aspects of it. And then zero inflated models, we will just discuss the theory completely, and we shall wind up over there. So this is the roadmap for our part 2. So if you have an output variable which has 2 categories, then it is by. By means 2. Whether an employee will churn or not, whether the customer will churn or not, will an employee treat or not, will a person purchase a specific product or not, will a person claim insurance policy or not. These are all binomial distributions. Binomial distribution is used when output has 2 categories. Sometimes we come across scenarios where our output variable has more than 2 categories. And if the output variable has more than 2 categories, you proceed further with something called as multinomial regression, which is obviously an extension to logistic regression. So you have logistic regression, and multinomial regression is an extension to that. Okay, now, here we have a scenario such as, if a person who gets down at the airport, especially in a lot of developed countries, we have this, right? You'll have the rail connectivity to airports, you have all the other connectivities. So what mode of transportation would people prefer? People getting down at an international airport, for instance, would they prefer to go by car, or would they prefer doing a carpool, or would they go by bus, or would they prefer rail? And when you look at all of these modes of transportation, say we have 453 overall modes of transportation. And this is simple count. You can also translate that into probability. Probably 218 divided by 453. If you multiply it with 100, you get in percentage, but then it's 0.48. 32 divided by 453 is 0.07. 81 divided by 453 would be this, so on and so forth. And when you add the probabilities of all the events, it would add up to 1. Okay. And when do you apply multinomial? Multinomial is nothing but multiple logistic regression. Okay, you can think about that as a multiple logistic regression. So here, when the response variable or output variable is more than 2 categories, we do that. But in this specific data set that we are going to talk about, what other inputs, independent variables are inputs, right? So here, output variable is which mode of transportation would people prefer? And the input variables are cost and time. How much will it cost if I were to travel by a car, or by a carpool, or via bus, or using rail transportation? How much does it cost? How much time would it take for me to reach from airport to home? is also something that we need to look at. And then we would look at this. This is the data set. Choice, which is your output variable. Would you travel by a car or a rail or a bus or a carpool? How much does it cost for each of the transportation, and how much would it take? How much time would it take? All these details are given to us. Okay, now, first thing is lowest in number or lexicographical value would be chosen as a baseline or reference. When you run the algorithm, you get the final output. For instance, you get an output like this. And this is an output from R. But then in Python also, you would get more or less the same thing. This helps me understand a few, help you all. It will help me explain a few additional things to you. That's why I prefer this, R output, R programming output. Okay. So if you run this algorithm, out of the 4 modes, what are the 4 categories? Would a person travel via car? Or would that person prefer carpool? Or would that person prefer a bus? Or would that person prefer rail? Right? This is what our business problem is. And here, car is not available. You have carpool, you have bus, and you have rail. So this car is considered as a baseline. Baseline level, because you have multiple levels in this output variable. If car doesn't appear, that means car is a baseline. Okay, so that is what this means. And you might say, hey, do you know what? We also have bus. And B comes before C. But then why is bus not considered as a baseline level? And why is car considered as a baseline level? This might be a question. So car is considered as a baseline level because you don't just look at the first alphabet. You look at all the alphabets when it comes to lexicographical sequencing. And only the first or only one alphabet comes first here. But when you look at U and A comes first. When you look at S and R comes first. That's called as lexicographical value. So the missing level is the baseline level. If you feel that, you know what, I don't want to look at the output with the reference to car. So now what happens is if this becomes baseline, interpretation of your coefficient values would be done with reference to car. How much would it cost to travel in a bus with respect to car? How much does it cost for doing a carpool with reference to car in comparison to car otherwise? How much would it cost me to travel by rail with reference to a car or in comparison to car? This is what we would be really interested in. And when you actually run the model, you try to establish the relationship between your output variable and your input variables. And this relationship establishment is very, very similar to what we have seen in logistic regression. There we just look at probability by 1 minus probability of an event occurring by 1 minus this, and we have taken a log of that, call it as log odds. and this is called as logic transformation. And we will see how the algorithm works here. So this is an output. When you run your algorithm, this is the kind of output that you see. And if you observe, there is some optimization going on. So if you have your curve like that, if your algorithm gets started over there, then you try to keep minimizing the error until you get to the minimum. So after a few iterations, as in how the initial value keeps on decreasing, you get to the minimum. Now, if you ask me, what is it that we are trying to minimize here? It is minus 2 log L. Okay, minus 2 log L is one of the AIC criteria. We'll talk about this later. Okay, when I actually talk about maximum likelihood estimation, okay, and that is when I'm going to talk about taking a log, okay, and then trying to work with the log of your likelihood. And then why do we take minus log L? Okay, and what do we actually minimize? We will talk about those things by getting into slightly, technical aspects. But of course, now that you have completed your data science training, it really makes sense for you to go that extra mile and then understand more. So anyways, we'll look into those aspects and we will properly look at the maximum likelihood estimation details. Okay, so I think we should proceed further. I have also made a note of a few of the important things, and I'm going to talk about those in further detail. Okay. So let me move on here. So you have the coefficient values, so on and so forth, interpretation and all that. So do I have the other equations already here? Yeah, here we have it. So I'll wait until we get there. So here, friends, what is the probability of an event occurring divided by 1 minus probability of not occurring? You take a log. When it comes to logistic regression, here we have multinomial. It's like multiple logistic regression. And if you look at these coefficient values that you see after you run the model, the level which is missing from this would be called as your baseline or reference. So K, which is missing from the 4 categories here, becomes your baseline. So you look at probability of choosing carpool given all your inputs, given the cost of the different transportation modes and given the time taken to reach the city from airport, right? For all the modes of transportation, given those inputs, what is the probability that your choice will be carpool? Okay. Upon what is the probability that you're going to choose a car given the same inputs? Given the same inputs, what is the probability of choosing a carpool over probability of choosing a car? This is how you write the equation. And you take a log of that, similar to our logistic regression. Now, given this kind of data or given this kind of equation, I mean, you can formulate other equations also. What is the probability of choosing a bus given the inputs? in comparison to probability of choosing a car given those inputs. What is the probability of choosing rail given inputs in comparison to probability of choosing a car given the inputs? And then you have a regression coefficient, which is 0.636. This 0.636, it indicates that for a 1 unit increase, okay, in the cost of the car, if I increase the cost of the car by $1, for example, the log odds, because when you take log of odds ratio, it's called as log of odds. This is called as simply put log of odds. Okay, now this log of odds of carpool to car increases by this. That means if you increase the cost of car by $1, the chance of you preferring carpool over car increases by 0.636. Okay, now say you have another column called gender. Out of in these inputs, you have another column called gender. Then assume you have a coefficient value of 0.22. What does that indicate? That and if female is 0, male is 1, that indicates that relative to females, instead of a female, if there is a male, the chances of the male preferring carpool to a car increases by 0.22. That means male passengers would prefer a carpool over female. That is what it means. By what factor? By 0.22. So the interpretation part is very important, my dear friends. The reason why interpretation part is important is because at the end of the day, we are building what? We are building regression algorithms. And why do people prefer regression algorithms? People prefer regression algorithms because regression has, the interpretation capabilities. Okay, that's the reason. Okay. So I would be at this point of time tempted to, draw the various equations and all that, because there are quite a few things that I want to explain, but let me refrain at this point of time. There is some more theory. Once I complete that theory, I would certainly get into some math derivations. Right? It should not scare you guys very early into the session, hence. All right. So you know about probability of an event occurring. You know about the odds. Okay. And this is also called as odds ratio, probability of an event occurring by probability of an event not occurring. Okay. And if you have, say, two conditions, like male and female, then the ratio is odds ratio of A with respect to odds ratio of B. Odds ratio of female in comparison to odds ratio of male. That's how you compare. And then you have relative risk. Relative risk is probability of an event occurring given female divided by probability of event occurring given male. So for example, if you have this status wherein you know that someone is a smoker, another person is a non-smoker, disease present, disease absent, and you have ABCD values. Probability of event when exposed means probability of an event where someone is a smoker is A divided by A plus B. And probability of event when not exposed rather, is non-smoker divided by overall disease present or absent. When you divide these two, ultimately you get something called as what is the relative risk that someone will have a disease given that they are a smoker divided by probability of someone having disease given that they are non-smokers. That's called as relative risk. Okay. And we also know for a fact that all these coefficient values are nothing but log values. When you want the actual coefficient values, you just take exponential of that. You exponentiate regression coefficients. And then you get the output. Here, once you take exponential and then if you get intercept values, or sorry, coefficient values, then the interpretation varies. Here 1.88 means the odds ratio for a unit increase in cost is this for choosing carpool over car. So in short, the chance of you preferring carpool over using a car increases by 1.88 if you increase the cost of the car by 1 unit. So you have probability of A, then you have probability of B, and you have probability of C. And if you add all of these three, it would sum up to 1. If you have three classes, probability of choosing a car, carpool, a rail. So probability of, I'll add one more thing because you have 4 levels. So this is equal to 1. If you know the probability of this, and probability of this, then getting to know probability of this is not difficult, right? So probability of D would be 1 minus probability of A plus probability of B plus probability of C. 1 minus this would give you probability of D. Okay, there are quite a few things which are written here. We would get back to this specific slide in further detail. Once we complete the multinomial regression code, once we complete the ordinal regression code that we run, then when we get into Poisson regression, that is when I'll talk about this part. Okay, which is also relevant. Whatever is given here, the AAC value, etc., is also relevant for logistic regression, and it's relevant for maximum likelihood estimation also. Because for linear model, we use something called as analysis of variance, residual sum of square, and then ordinary least square technique. Here we use something called as residual deviance, maximum likelihood estimation. But what is maximum likelihood estimation? We would take it in the context of Poisson regression, because there it is a lot easier. Okay. So let me run the Python code, and Python code, etc., is a walk in the park. It's extremely simple here. First of all, we need to import all the required libraries. We are importing pandas, which is used for data manipulation purpose. We are importing Seaborn, which is advanced data visualization technique. And we are importing train test split, which is used to split the data into training and test. Then we are importing logistic regression, because whatever we are trying to build is multinomial regression, which is an extension of logistic regression only. Then we are importing the accuracy score. Here, let me go to the data set called mode. and we read this dataset called mode.csv, you load that into mode. In this mode dataset, you have 453 rows and 9 columns. Out of these 9 columns, column number 1 is choice. When it comes to choice, you have car, rail, bus, carpool, etc. Okay, if you say header 5, for instance, you get to see the first 5 rows of the data set, just to have a glance at the various columns which exist. When you say mode.describe, here we are loading the dataset as mode.describe. For all the numerical columns, you would get to see the minimum value, maximum value, 50th percentile, 25th, 75th, standard deviation, mean, so on and so forth. When you say mode.choice, .value counts, you're saying that you want to go to this dataset called mode. In that, you want to go to the column called choice, in which you have various values and counts. So you have the 4 values and you have the counts of that. Okay. Then you have SNS. SNS is Seaborn. And you're saying SNS.boxplot. So here X is choice, Y is cost of car, data equal to mode. Okay. Here, when you look at choice, you have car, rail, bus, and carpool. And on the y-axis, you want cost of car. And then you're saying data, you want to use this. Now, by looking at this, you should be able to figure out on what's going on exactly. If you look at the median of cost of car, it's much less in comparison to rail, bus, and carpool. So the cost of car is less, the median cost of car in comparison to all these three. The next least is bus, but then bus, rail, and carpool costs, median costs are more or less the same. So these kind of insights you can draw the moment you have the different calculations. You can draw the box plot for each, and then you can draw inferences from each of these. Okay, next. Once you draw inferences for each of those, you also have a scatter plot. When I say jitter equal to true, so what we are doing is we are coming up with something called a strip plot. Again, on x-axis, you're having choice. On y-axis, say you have cost of car, jitter equal to true, and data you want to use it from this mode. This jitter, what it does is it's going to just, if you have a same value, for example, here 2, and if you have multiple values, right, it's just going to show all those multiple values by segregating those. It won't overlap one on top of another. Okay. For example, say you're here somewhere, right? So if you have multiple data points, all those data points would not get combined into one. For example, if I change this, if I say jitter equal to false, for instance, and if I were to run it, it appears like this. So if there is a specific point and if there are multiple such numbers, all of those will be one on top of another. Jitter means it will just jitter them and show you the distribution. Okay, this is also another plot to see what is the kind of dispersion we have. Okay, next. We also have a pay plot. Pay plot would actually tell you what is a histogram of each and every column. And it would also show you the correlation between various variables. So you have histogram of each and every column so that you understand whether here it is almost uniform distribution. Means the probability of each event occurring is equally likely. Here it is normally distributed. That means probability of events occurring here would be higher than probability of events occurring at the tails. Okay, you can get you get to see the correlation. Okay, time of carpool. And what is this column actually? Let me zoom it and see. And time of car. It's almost same. The amount of time it takes for a carpool or car is almost the same. There's very strong correlation out there. So these kind of things you can draw insights about. We just say hue equal to choice. What is the choice that we have here? Car, rail, bus, carpool, etc. For each of those, it is going to show you a different probability distribution. Okay. So if I were to run it, let's see. For each choice, it should show me a different probability distribution. It's taking time. So yeah, there we go. Yes, absolutely. So when you say pay plot, obviously it is showing in the pay plot. However, you have the different choices given in different colors. And for car, what is the kind of correlation that we see? For the rail, what is the kind of correlation we see? For bus, what is the kind of correlation? For carpool, what is the kind of correlation we see? Everything is clear. And you also have probability distributions, right? Here, when it comes to car, it is actually like it has a very high kurtosis. Next, rail has kurtosis. Everything is normally distributed, but then bus has a negative kurtosis, and the negative kurtosis is greatest for carpool. These are the kind of things that you can draw insights about. Okay. You can also see, friends, whether a specific plot is a univariate plot or a bivariate plot depends on only one thing. Are you doing a plot for a single variable? If yes, then it is univariate. If you're doing a plot for multiple two variables, it is bivariate. And if you're doing a plot which includes more than two variables, then it's called as multivariate. Simple. There is nothing complicated here. Given this logic, what are we trying to do? What do you think is a strip plot? What are the two things that you're choosing? Choice, which is either carpool or etc. And then you're also looking at the cost. When you look at two variables and when you plot it, what would it be called as? Would it be called as biplot, bivariate, or univariate? Right? So it is bivariate. Okay. You can also look at the correlation coefficient values, and you're saving it in A. If you were to launch that, you get to see the correlation coefficient matrix. Obviously, you know how to draw the inferences. One thing which certainly catches my attention at this point of time is this value, which is the correlation between time taken for carpool versus time taken to car. It's almost the same. Okay. Now let's split the data set into training and test. 20% of data is randomly getting split into training. Another 80% would be part of test. So you have training data set and test data set. And here you're saying, let me run a logistic regression model. However, I would say multi-class equal to multi-normal. Okay, so whenever you have multiple output variables, categorical variables, you go ahead with multi-normal. And here, when it comes to solver, this is one kind of an optimization technique where you have various techniques such as Newton-Raphson technique. There were two scientists. One person was Newton, another person was Joseph Raphson. They both have come up with some technique, some optimization technique, basically. Whenever you have nonlinear equations, when you want to find the solution pertaining to that, people use this Newton-Raphson technique. Okay, and this Newton CG that we are seeing there in the function is one of those optimization techniques. Alongside that, you also have LBFGS, limited memory, and this BFGS are the four scientists: Broyden, Fletcher, Goldfarb, Shano. Against their names, they have named it as BFGS algorithm. Usually it is BFGS. And we also have a variant of that, which is called as LBFGS. It's called as limited memory. This is also another optimization algorithm. Optimization algorithms, what is the goal of those? The goal of those is either to find a minima or maximum. In this case, it would find you minima. It will help you find the minima. Okay, a lot of gradient algorithms are gradient descent algorithms. They'll find the minimum. Okay, that's how they formulated it. Of course, with small changes, you can also find the maxima, but that's how it is. Even Newton CG technique. Yeah, CG is nothing but a conjugate gradient. It's one of the gradient descent algorithms. Okay, so if it is a gradient descent algorithm, then what should you find out? Minima. So you should minimize something. That's the goal, right? You should be in a position to minimize something. When, how do we minimize it, etc.? We will talk about it. We are getting there. We will get to the equation and all that. Okay, why do we take -2 log L? How is it related to AIC? Why do you think least AIC is the best? We'll get there. So when you try to build the model, you're saying, let me fit the model by taking the training data inputs and training data output. When you go to training data, only the first column, which is index number 0, would be your output. From 1 until n would be your inputs. So you run it. Then you take your model and say predict. Predict your model on the test data. Predict your model on the test data, and then you get the predicted values. You have all the predicted values, whether someone will prefer carpool, etc. Okay, so what are we doing here? We are trying to compare the test predicted values with the test actual values. If I were to go to test data, column number 0 has the actual value. So when you try to compare it, you get the accuracy. Accuracy is 0.703. Okay. You can also predict using the model that you built on the test on the training data set. You get the trained predicted values. When you try to compare the predicted values and actual values of the training data, you get the accuracy score, which is 0.68. So 0.68 and 0.7, of course, they are very close to each other. So you can see that it's a right fit model. And the reason why we are not doing all the pre-processing techniques is because that would remove the attention from the main algorithm. Right? However, when you look at this CRISP MLQ, we are talking about predictive modeling techniques and regression models, right? So the assumption here is that you have already traversed phase 1 and phase 2, and within phase 2, I'm assuming that you would have done exploratory data analysis, you would have done all of these data cleansing techniques, and only then you would have gotten into this phase. So if I take the data and start applying all the data cleansing techniques, probably the majority of the time we would be spending only talking about data cleansing. But our focus here is to understand the algorithms, right? Hence, I'm talking only about the algorithms. But whatever data cleansing techniques are there, you need to look into that. What does accuracy depend on? Here, if you feel that 68% is low, what does accuracy really depend on? Accuracy depends on various factors such as how much data I have. Here we have a very limited amount of data, 53. That's a small data set. Why are we using such a small data set? Because our attention is to, our focus is to understand the algorithm, how it works. If you have more data here, obviously your accuracy will be much better. Point number one. And also you have a lot of hyperparameters. You can try out, experiment those hyperparameters. When you just say health of logistic regression here, you have a lot of things which exist, a lot of hyperparameters. You can read and play around with those hyperparameters and see which hyperparameter is actually giving you the best result. If I were you, I would have probably tried out, L1, L2, elastic net as a penalty term. I would have probably tried to look at intercept scaling. Maybe I would have tried different solver techniques which exist. Right? In that way, I would have probably experimented with different options. Okay? Because that would actually give me enough confidence that I've tried various experiments and this experiment is working well. All right. So this is multinomial regression for us. Let me delete this stuff. Ordinal regression is a very, very small extension of this, and it is something which usually doesn't give you a result much better than multinomial. Even if you have ordinal data. Okay, so when you look at the data set, when you look at your output variable, if it is nominal, you proceed further with multinomial. If it is ordinal, you proceed further with ordinal regression. Multinomial regression. And when it comes to ordinal, you have ordinal regression. Okay, so you have multinomial regression and you have ordinal regression. Okay, then so we discussed about this, but switching to ordinal regression usually doesn't give you any better result. Even if you have ordinal data, right? People usually treat it as multinomial, nominal data and proceed further with multinomial regression. Why do they do that? Because usually the results are not so profound. It doesn't warrant that you try out different set of algorithms. Okay, next. Whenever you have a sequence like satisfaction score, customer satisfaction score, 1 means poor, 2 means moderate, 3 means good, for instance. In those kind of scenarios, people use this. Ordinal regression. Okay, then when it comes to ordinal regression, there's only one small thing that you need to remember, and that one small thing is that you divide your data set into only two parts. Let me show you. If you have more than two categories, and if there is a sequence, you proceed further with ordinal logistic regression. And if you have categories with a natural ordering, we usually proceed further with that. Here also, you'll have a baseline or a reference, which is chosen based on lexicographical value or using numerical data. If you have government policies for people below poverty line, then too little, about right, and too much. Right? Policy can be classified as whether it is doing too little to the people below poverty line, or is it about right? The government policy is it about right? Or is the government policy too much? Too much is also too bad. Okay, so based on religion, based on degree, based on country, age, gender, probably you're looking at those aspects. Okay. Survey, these are survey results on policies implemented for poor people in the country. Is it doing too little or about right or too much? This can be arranged in a sequence, ideally, right? And you can just divide the data, which is this J, if I were to treat this as J, as what if your output variable is less than or equal to J, given probability of your output variable greater than J. In multinomial regression, if you remember, we were looking at what is the probability of output variable being, say, for example, carpool in comparison to car. But here, it's slightly different. Here, what is slightly different? If you have three levels, say level 1, 2, and 3. 1 means too little, 2 means about right, 3 means, too much. Then you treat 1 as one category, these two as another category. What is the probability that government policies on poverty is too little in comparison to probability that government policies for poor people being about right or too much? So this is like less than or equal to J. J is this value. Greater than J means greater than 1, which is 2 and 3. Okay, this is how it works. So always, you'll have here alpha and beta. That's beta naught and beta 1 basically. Why we segregate in that way? Because we are doing only two comparisons. And this is the kind of output that you get when you run your algorithm. Okay, and if you have, for age example, if you have 0.01114, how do you interpret that result? The interpretation is that 1 unit increase in age for every 1 unit. I mean, if you increase the age by 1 year, then the log of odds of positive feedback increases by 0.01114. Your output is to know whether it is too little or about right or too much, right? So this is what you get. Okay. When it comes to intercept values here, too little by about right means it is for y less than or equal to 1. This about right given too much in comparison to too much would be called as probability of y less than or equal to 2. You try out with various combinations. Okay, so there is nothing much about logistic regression beyond this. Then you have, odds ratio and the different discussion. So if you have too little in comparison to about right, then the log of odds of government doing too little versus the government doing about right or too much. So you're classifying these two into one. Too little as 1. Too little, about right, too much. Either do in this way, compare this with these two, or compare this with these two, or compare this with these two. Okay. So that's it. Nothing much pertaining to ordinal regression. So let's run the code. The code is also pretty straightforward. Let me take this WVS dataset and load that. After this, we'll get into some amount of calculations, math derivations, which will actually give you immense control and confidence. Let's see. So we are importing pandas as PD, scikit-learn pre-processing as label encoder, scikit-learn matrix as accuracy score, and you're loading this WVS dataset. Okay, then if you were to look at the head, you see poverty. Okay. Is government doing too little or about right or too much? Given specific religion, degree of the people, country, age, gender, so on and so forth. Here, degree does not mean your education. To what degree? I mean, are you really crossing the barrier, yes or a no? That's what it means. Okay. Then you can say dot describe. For only numerical variables, you'll get this. Only age is a numerical variable, so it's saying minimum age of the people who are giving responses is 18, and the people, the maximum age of people who are responding to the survey is 92. You can also look at the various columns. You have poverty, degree, religion, degree, country, and gender. You can also do a label encoding. It's up to you whether you do label encoding or whether you do one-hot encoding. In our case, we are just doing a label encoder. Fit_transform would actually apply. So we have performed that. Now there is a library called as mod, which will help you perform ordinal regression. Yeah, this is what I was assuming. I haven't installed this library mod. Let me install that. So I'll go to the terminal. Let us say pip install mod. When you do that, it's going to install the library called mod. Okay. All right. So let me go back here. Let me try importing this library. Yep, it will. Here, logistic 80, which is nothing but ordinal, alpha equal to 0. When you say alpha equal to 0, you are saying that I do not want to perform any regularization, because you have, alpha equal to 1, alpha equal to 2. Let me run that. Those are all regularization techniques. Okay. 0 means no regularization. 1 means L1, L2 means 2, so on and so forth. Okay. Then you're saying, let me fit the model on inputs and output. Column 1 is the input, rest of the columns are, column 1 until end are inputs, and index number 0 is your output. So you build the model. Then you have the model coefficient values. You can look at the classes. You have 3 classes, 0, 1, and 2. Then you're saying take the model and predict on the inputs. Then you get the predicted values. Then simple, compare the predicted values with the actual values. Here, the data set, I mean, obviously, we could have split the data into training and test, and we could have built that. That was pretty much possible. But the point that I'm trying to drive here is the accuracy of the model is very low. So Not that, ordinal regressions would often give you wrong results, or it will give you less accuracy over nominal. That's not the point. But usually your multinomial regression gives you good results. Even if it's ordinal data, just apply multinomial as well. But then by doing that, you are losing out the effect of order. In this data, you have a sequence, you have an order, right, of poverty. You have that sequence. Sequence is too little, about right, too much, right? That sequence order will be lost. Sometimes that order is very, very important, even if you get this, even if you get slightly less accuracy. Okay. Now, we need to get into the count models. Poisson regression. This is the probability density function for binomial distribution. Binomial distribution. Okay, and for binomial distribution, mean is given as NP. Standard deviation is given as square root of NP into 1 minus P. Here is a classic example, and then you can say you're a data scientist in electronics manufacturing plant. Historically, the USB device, USB manufacturing process is shown to yield about 6% defectives. Find out if the specification limit is exceeded, right? And for each day producing exactly 50 items. So number of trials is 50, P equal to 6%. Then mean is nothing but NP, which is 3. Then you have negative binomial distribution, for which you have a density function of probability function here. This is how you calculate the probabilities, but we have again Poisson distribution. For that, this is the probability density function. You can go through this whenever you find time, because these probability distributions are important for us to understand the different probabilities. And then you have various questions here for your practice, for your quizzes, to understand which one is Poisson, which one is binomial, etc. Bi means 2, right? Probability of loan defaulting, will person default or not? Probability that one component of truck is defective or not? Probability that the person is married or not? These married or not usually people use in advanced dating websites, in which you'll be able to predict certain things. And then you have Poisson distribution, which is find the number of flights arriving at airport during a 15-minute period. So always it is given a time period or given a specific region, area. Within that, you want to find out. Find the number of carbon particles in cubic meter. This is important, cubic meter of air. Determine the probability of call center having more than 50 calls in 1 minute. So 1 minute is important. So within a specific duration or specific region, you want to find out the count. Okay, and here we have Poisson distribution. So even before we get into Poisson distribution and offset, and you have excessive zeros and count models, dual models, hurdle models, zero inflator. And okay, I'm just looking at all of that, but I would prefer to write down and then explain. 2 or 3 things that I want to quickly explain you all. Number 1, suppose you have a random sample. Suppose you have a random sample of, okay, you have some random sample of variables from Poisson distribution. This Poisson distribution, let me call it as lambda. not Poisson distribution, from some Poisson distribution with some parameter lambda. Like when you have your normal distribution, you say that a random variable is normally distributed, approximately normal, this random variable, given mean mu and variance sigma square. In that way, for Poisson, you have a parameter called as lambda. Okay, now. Say you have number of insurance claims. Number of insurance claims. X1, X2, X3. So you have all these insurance claims. Assume that all these are independent of one another. If the number of claims is like 40, 50, 60, if they're big numbers, my dear friends, we can as well use it as, you can treat that as a continuous variable. And you can proceed further with linear regression also. But if the number of insurance claims is like 0, 1, 2, 3, 4 in that way, then certainly you need to go with one of the count models. So Poisson regression is a count model. You have here count. 1 insurance, 2 insurance, you have the count. The probability values associated is the probability density function pertaining to Poisson is given in this way. E raised to the power minus lambda into lambda raised to the power x by x factorial. Since you have x1, I'm writing. For x2, you'll have on similar lines this formula, and then if you have xn e power minus lambda into lambda raised to the power xn divided by xn factorial. Now let me erase this part. If you want probability of x1 until xn given lambda, given these parameters, if you want to find the probability of this, then you need to multiply all of these probabilities. And if you were to multiply all of these probabilities, okay, then what would you get? You get product. Summation means sigma. This is product of I equal to 1 until n e raised to the power minus lambda into lambda raised to the power xi divided by xi factorial. If you substitute 1, you get this. If you substitute 2, you get 3, n, so on and so forth. This can be written as, you can bring this out, it'd be e raised to the power minus n lambda into product of I equal to 1 until n lambda raised to the power xi divided by xi factorial. Okay, this is what we get. And there is one more thing that I want to tell you, that why do we get lambda, if that's your question, right? So let me give you, if you have a variable which is approximately Poisson, you say that with parameter lambda, and probability density function for Poisson distribution is e raised to the power minus lambda into lambda raised to the power x by x factorial, and x can be count 0, 1, 2, so on and so forth. If you were to add all the probabilities, you get summation from x equal to 0 until infinity, e raised to the power minus lambda into lambda raised to the power x by x factorial. If you bring this out, you get e raised to the power minus lambda. Then you have summation of x equal to 0 to infinity, lambda raised to the power x by x factorial. And you know what? This is nothing but an expansion of e raised to the power lambda, this part. If you remember your school days, there's nothing but 1 plus, I mean, if you substitute x equal to 0, lambda power 0 is 1, by 0 factor is 1, 1 by 1 is 1, plus. If you substitute x equal to 1, lambda raised to the power 1 is 1, by 1 factorial is 1, plus lambda squared by 2 factorial, so on and so forth. This is nothing but e power lambda. Now these two would be e power lambda minus lambda plus lambda. This will become 0, which will become 1. Okay. Ideally, correct, you need to get 1. And hence, the expected value of x is nothing but summation of x equal to 0 until infinity, x into probability of x. X into probability of x is this part. Expected value is x into probability of x. So probability of x is this value. So write down e power minus lambda, lambda raised to e power by x factorial. And when you solve it, you ultimately get lambda. Okay. So expected value of yi, if you look at this, is nothing but lambda. And here, variance of this is also equivalent to lambda. If you solve, you'll try to get this. I mean, if you solve, not you'll try to, you will get this ultimately. Okay. Now I've written that equation just for some clarity on where that lambda value is coming from. Okay. Now, that's the story behind the scenes for Poisson distribution. Whatever you are able to observe, friends. You need not consume everything, not needed. Whatever you can eat, you eat. Whatever you cannot, throw it out. That's it. These are all additional things. No one would ask you these things in interviews, but having knowledge about these would help you, certainly. Going back to our discussion here. So given this, the question that we need to ask when it comes to maximum likelihood estimation is, what is the value of lambda? What is the value of lambda which makes the observations, that is probability of x1 all the way until xn, most likely? Okay, what is the value of lambda which makes observations most likely? Okay, or if I were to frame it again in a different way, find lambda such that probability of all of these given lambda is largest. And here you can say L is equal to probability of x1 all the way until xn given lambda. And this is a L is used as a function of lambda. That is, L of lambda is equal to e power minus n lambda, this part, into product of I equal to 1 until n, lambda x raised to power I by xi factorial. Now our goal is to maximize L. Maximizing L, for some math comfort, people use log of L. So maximizing L or maximizing log of L would give you the same solution. This is because log L is an increasing function of L. That means wherever you have maximum L value, log L also will be maximum. Okay, log L also would be maximum wherever L is maximum, because log L is an increasing function of L. So that means if you maximize L, you get the maximum value. If you maximize log of L also, you will get the maximum value. Okay, next. Okay, I mean, I'll talk about a few more transformations at a later point of time, but then if you take this and if you take log of L, if you take log, what happens is this part, log and exponential get cancelled. You get minus n lambda plus product will become summation basically. I equal to 1 until n xi into log of lambda. This xi factorial, etc., would remain the same for all the equations. For all the other values, this xi factorial will remain same. It won't change. So I'm not representing that simply. That's the only reason. Okay, and also another reason is this xi factorial doesn't include lambda. So we can ignore that. Now, this is the first order. I mean, this is the equation that you're getting by taking log on both sides. Now you find the first derivative of this and equate it to 0. When you find the first derivative and equate it to 0, what would you get? You will get the critical value. Then to figure out whether that critical value is minima or maxima, you need to do a second derivative. So if you do a first derivative and equate it to 0, you'll get lambda value, which is nothing but critical values. Now, if you take derivation of this, d by d lambda of log of L lambda, what do you get here? Minus n plus sigma of xi divided by lambda. That's what you get when you find the derivative of this, right? Log x derivative is 1 by x. That's what we're getting here. This will remain as is. When you solve it, you get lambda is equal to x bar, because you get summation of xi by n. This n would come here, lambda will go there. This value is nothing but x bar, mean. Right? That is why we have said here that mean of Poisson is lambda, variance of Poisson is also lambda. Okay, so mean and variance would be equal. This lambda raised to the power this is nothing but residual deviance. Okay, it's also called as what? Residual deviance, which is approximately equivalent to your R squared value. But even before that, maximizing this log L is also equivalent to minimizing minus log L. Hey, why do I need to minimize? Why can't I just maximize? Friends, we minimize because a lot of gradient descent, a lot of optimization algorithms are gradient descent. They would minimize. Okay. So, and also, if the L value, whatever you get, probability values, right? L value is nothing but probability values. If probability values range from 0 to 1, then log of L would be negative values. Negative values don't make sense. So you take negative of log L, and negative of log L would be having positive values. Okay, this is another reason. Okay. But ideally, we want to minimize it. Why are we taking minus log L? To just get the positive values. And then here, usually it is not minus log L. People take minus 2 log L. Why do they take minus 2 log L? They take minus 2 log L because minus 2 log L statistically follows a chi-square distribution. There is some probability distribution called as chi-square. Okay, just because that advantage exists, right, people use minus 2 log L, which is approximately similar to your chi-square. Write it as chi-square. Okay, and that's the reason why people take that. And you know what? Minus 2 log L is called as AIC criterion. It's not exactly AIC value. It's called as AIC criterion. It's just a AIC penalty term. You can think about it as some kind of a penalty term. But ideally, AIC value is minus 2 into log L plus 2 times of number of parameters that you have in your model. So if you have to minimize this, minus 2 log L also should be minimized. So AIC also should be minimized. Hence, AIC, the least value is better. This is the entire logic. We keep saying, right, that it should be the AIC value least the better. From this logic is what you're getting at. Okay. So given this discussion, you now understand probability distribution and maximum likelihood estimation. Okay, and what we are trying to maximize is nothing but LP or log of LP. But since a lot of algorithms go based on variant descent, we are taking minus log L and we are trying to minimize that. Okay, when we do minus 2 log L plus 2 times of parameters, you get AIC value. And that model which has the least AIC value is considered to be the best model. Okay, these are a few math stuff that you need to be aware of. A few more things I will write here. Point number 1. Poisson regression has an underlying assumption that mean should be equivalent to variance. This does not mean that I'll go to my data set, I'll take my output variable, take mean of that, take variance of that and compare. No, that is not what I'm saying, right? So you cannot do that kind of a direct comparison. You need to get expected value and expected variance values. So usually what people look at is if your dispersion parameter, when you run your algorithm, you get something called as dispersion parameter. In this dispersion parameter, if this value is equal to 1, that implies mean equal to variance. Point number 1. Okay. And we have another thing called as residual deviance. Residual deviance is a proxy to R squared value. Okay. And if your residual deviance value is greater than your degrees of freedom, when you run your algorithm, you also get degrees of freedom. Okay. That is n minus number of parameters that you have, right? If the residual deviance value is greater than this, it implies that variance is going to be greater than mean, and this implies over dispersion. And when you have over dispersion, Poisson algorithm doesn't work well. In which algorithm works well? Negative binomial. Negative binomial algorithm works well. Okay. So you prefer negative binomial over Poisson regression. But ideal scenario is that if you have count model, try out Poisson, try out, there's something called as Poisson variant, which is called as offset. Poisson with offset. And you try out something else, which is called as negative binomial. Poisson regression has a condition mean equal to variance. And when the dispersion parameter equal to 1, this is what it means. Or when residual deviance equal to degrees of freedom, or residual deviance value if it is close to degrees of freedom. Residual deviance if it is close to degrees of freedom. Then that means you are running Poisson regression. However, if residual deviance is greater than degrees of freedom, that means variance is greater than mean over dispersion, you proceed further with negative binomial. These things are clear. Variance greater than mean. Now this Poisson with offset is something which, you know, we all should be very aware of. So, okay, let me give you a few examples here. If you have an output variable and if you want to look at number of claims, number of insurance claims, these number of insurance claims would actually, I mean, maybe you included a lot of input variables, age, gender, so on and so forth. But then if you're given, or if you have more insurance amount, if your insurance policy has, you know, $10,000 as insurance, or $20,000, or $30,000, depending on how much money you have. If you have more money, which is covered as part of insurance, that means maybe you will claim frequently because you know that you have a lot of money to be claimed. So you, for every small thing, you go and claim insurance. So if the number of claims depends on insurance amount, you can either treat this insurance amount as an offset variable, or you can include this as another input. Either way, you need to include the effect of this, like confounding, moderating variable, etc. Or if you're trying to predict the total debt of a person, output, and you have various inputs, age, gender, income, education, so on and so forth, right? So, sorry, not age, gender, education, whether you have previous loans or not, given all that. Then you might feel that, you know what, I have another variable called income. If someone has more income, they might take more debt, maybe. Or the income and debt might be correlated. So you might want to consider total income as an offset variable. Okay, you might want to consider that as an offset variable. On similar lines, say you want to predict the total card payment. Okay, you want to do the total card payment. But for this, you might also, or let me look at card balance. You are using a credit card and you have some balance. After using your credit card, every month, you'll have some debt and some balance. Someone might have 10,000, someone might have 20,000, someone might have 30,000, but that won't give the complete picture until and unless card balance is 30,000 out of 40,000. Is it that way? Or the total card balance is 80,000 based on, 200,000 that you have, right? So the credit limit, the amount of credit limit that you have, if someone gives you a credit card, they'll say, hey, you will have a limit of 400,000, right? Or 100,000. Until then, you can use it. 1 lakh rupees, 2 lakh rupees, 4 lakh rupees. Until then, you can use it. Depending on that, you use the money. And that has an influence on how much money you will leave as a balance. If you have 10 lakhs, maybe you might want to use 6 lakhs and 4 lakhs might be a balance. That balance is dependent on credit limit. So you need to have this additional variable. These additional variables are called as offset variables. Either you use them as offset variable in your regression Poisson, only in Poisson that's applicable, or use these additional variables as inputs. Use them as an additional input within your data set. It's up to you. Okay. So I think with this theory, with this understanding, we shall now proceed further with Poisson regression and negative binomial regression. And once we are done with this, we shall, in theory, talk about zero inflated models. What do you mean by zero inflated models? But even before that, one more discussion. If you have a variable, an output variable, right, which is say number of claims. And if this number of claims, number of insurance claims, if it follows Poisson distribution, then you can make this normal. And then you can apply maybe linear regression. Here, if it's Poisson, maybe you'll run Poisson regression. And here, maybe you'll run linear regression. But then before running linear regression, you take this and how do you make it normal? Maybe you take a square root of y. All the values will become small. Okay. Or, I have to probably explain it the other way around. So if you have a variable which is actually having big numbers, like, someone has done 200 claims, 180 claims, so on and so forth. If you take a square root of these, that value becomes smaller. And then you can apply Poisson regression on that. This is called a square root transformation. If you have a variable which has count values which are very large, you can as well apply linear regression and it will work well. But if you believe that this is count data, I don't want to go ahead with linear regression, then do a square root transformation and apply Poisson regression. Or there is a special transformation which is like this. And this is called as Freeman-Tukey transformation. Okay, Freeman-Tukey transformation is you take square root of that plus square root of this and then perform. Okay, there's one thing. And whenever you want to take a log transformation, remember one thing, that since it is count data, number of insurance claims, if they are 0, log of 0 is undefined. If the number of claims is 0, log of 0 is undefined. In these kind of scenarios, you take log of y plus 1. Even if you have a number 0, you make it 0 plus 1, and log 1 is at least 0. That's acceptable, but log 0 is undefined. That is probably not valid. Okay. So is there anything else that I want to talk about here? I think that's it. these should do. And then I'll talk about zero inflated models, which will probably take very less amount of time. So let's go ahead with Poisson regression and negative binomial regression. So I'll remove everything which is available here. Take Control L. So we are importing various libraries in which we have pandas, we are importing Poisson, and we are importing negative binomial. Let's take the number of claims. So pandas.read_csv, you read the file and you load it into claims. And when you say claims.head of file, you see that you have number of claims, number of vehicles, age, etc. If you were to take all the inputs out, or if you feel that the ID number, insurance ID number, application ID number doesn't matter, you exclude that and you say, let me go to all the other rows and columns from 1 until end, store it in claims. When you say claims.describe, you get to see number of claims, number of vehicles, age. Number of claims are from 0 until 6. You can also look at number of claims. And if you want to look at the unique values, it says 0, 1, 2, 3, 4, 5, 6, and that way. You have a lot of unique values. You can look at the values. 0 claims is 124, 149 people have done claims, insurance claims once, 13 people claimed twice, so on and so forth. Then you have a Poisson regression, Poisson, y tilde x1 plus x2. And if you want data equal to claims data set, fit, storing it in M1 and simple Poisson regression. And when you say print of M1.summary, you get to see the results. Yeah. And yeah, this is also based on what? Maximum likelihood estimation. We discussed about that. Log likelihood. Yep. We discussed about this as well, log L. But our objective is not to deal with log L. Our objective is to deal with a different value, right? And that different value is, what is that value if someone remembers? Not log L, it is minus log L, minus, it's not directly minus log L, it's again minus 2 log L, because it follows chi-square distribution. Yes. So we have the intercept values, you have the corresponding p-values, write down the equation, use your model and predict on the data set. You get the predicted values. If I go to claims, I can store this claims in something called as model._fit. Another data frame is what I'm creating, in which I'm adding a column called pred claims, and I'm adding all these predicted values to that. Okay. And then you can look at this, wherein I have all the predicted claim probability values. Okay. And if you want to use negative binomial, it's very simple. Negative binomial of y tilde x1 plus x2. You want to build the model on the claims data set. You have a very small data set here, 200 observations. So I'm not splitting it into training and test. And if you look at the results, once again, you have log likelihood value. From that, you can figure out whether your model is good or bad. And then you have all the coefficient values, corresponding p-values. We can use a model to predict on the data sets. You have all these predicted values, which are nothing but probability values. Now, you're replicating this claims data set and you're putting it in model_fit2. And here you're taking all the predicted naive-based values and loading it into another column called NV_predicted. And there we go. So almost the Poisson and negative binomial regression prediction values are more or less the same, if you observe. They're more or less the same. So that also gives us confidence that the model is working well. Okay. So now let's quickly talk about the other algorithms. For that, let me go to documents here. Let me open all regression techniques. Okay. Now, yeah. So in a few of the scenarios, like number of insurance claims itself, your data might have too many zeros in the output variable number of claims. You might have a lot of zeros. That's called as inflated zeros. When you have these inflated zeros, your regular Poisson or negative binomial might not work. You might want special type of algorithms, special types of algorithms rather, which will be able to handle these excessive zeros in a better manner. Okay, so to handle these excessive zeros in a better manner, we start treating all those excessive zeros separately and the non-zero values separately. So you might say that, okay, let me do one thing. Let me build one algorithm for all these zeros. Okay. And I'll take all those zeros and I'm going to model those zeros. Okay. Using probably some kind of different algorithm. For example, if you look at zero inflated Poisson, all the zeros are built using probably some different algorithm. You know, what example can I give here? Okay, so or let me put it in that way, this way, that in every zero inflated algorithm that you build, right, you can simply say, I want the distribution to be Poisson. If you give the distribution as Poisson, the zero inflated model becomes zero inflated Poisson. And alongside this, you also have to mention link function. And if you say link is logic, for example, what your model does is it is going to pick all the zeros and ones, in your data set, and it will start treating this as two-class problem, and it will build a logistic regression. And 2, 3, 4, all these count values would be given to your Poisson distribution. Okay, this is how you build. So if you have all these values, you only take zeros and ones, start treating them as two-class problem, and build a logistic regression using this link function. And you take all the other values, 2, 3, 4, etc. Start treating them as different distribution and build a Poisson regression. If it is zero inflated negative binomial model, once again, there are two things that we need to mention. What is the distribution? If you say, I want to go ahead with negative binomial distribution, you have in this way. And link function is logic. Okay. Then what happens is all the zeros and ones in your data would be taken and it will be treated as a different data set. And you end up building a logistic regression model. All the other values, 2, 3, 4, 5, all the other values, count values will be taken and you end up building a negative binomial regression. Okay. Then what do I do? Then aggregate these two results. Whenever you build the model, just take the mean average, supply the inputs that you have, age, gender, income, all that, supply to both of these models. You'll get two models, right? You'll get model 1, which will be on this, and you'll have model 2, which will be negative binomial on this data. So supply these inputs to model 1 also, you get some output. Supply these inputs to model 2 also, you get another output. Take an average of those two. So you get output from model 1. You also get output from model 2. Take an average of that. When you take an average of that, jump down. You get the final output. Okay. Then, if you build, instead of zero inflated Poisson or zero inflated negative binomial, there is another model called as hurdle model. It's a different set. It's a different algorithm. When you build your hurdle models, same thing, you give your distribution as Poisson or negative binomial, and there'll be an option called zero. For zero also, like link function, there'll be something called a zero. In zero also, you mention what algorithm do you want to use? Do you want to use Poisson or you want to use negative binomial? Which option do you want to use is something that you can mention upfront. Okay, so that's the thin line of difference, right? Both of these work on a similar fashion, zero inflated models and hurdle models. Okay. So this is the difference. And one thin line of differences in zero inflated models. Your model will look at all the zeros and ones only if the number of zeros are more than a specific proportion, then it will take the zeros out. But in hurdle model, it will directly segregate your zeros and ones into zeros and non-zeros into two different data sets. And on zeros, it will build one model. And on all the count values, that is non-zero values, it will build a different model. Okay, so hurdle model has two processes, one for all the zeros, one for all the non-zeros. Okay. So these are a few things that you need to remember. And of course, when it comes to regression techniques, there are huge number of techniques that exist. But whatever we have just learned is more than sufficient to handle all the data sets. So you now have the power to understand what algorithms you need to use when output is continuous, when output is discrete in two categories, discrete in more than two categories. When you have count, what do you do? If in the count, if you have too many zeros, what do you do? And if your model overfits, how do I handle it? You have all these regression techniques at your disposal. So please use it judiciously and make the best use of that. Okay. So I will stop here. And while there are a lot of other techniques, why do we usually bank on, these kind of advanced regression techniques? The only reason being it has the power of interpretation. If you can interpret the model parameters, then you can go and explain your model to the end users. So the explainability also increases. With this discussion, I will stop. And thank you so much for attending the session, friends, and all the best for your future. Thank you all.